Okay, let's look at our second example. You say determine the equation of the plane that contains the points P, 1, negative 2, 0, Q, and R. Before we can determine the equation of the plane, we need a normal and then one of the points. So where the normal will meet that point. So we first need to find the normal. And now these are 3 points on the plane. So we can find any 2 vectors on the plane. It's good when you make the points, all the vectors meet at the same point. So I can find the vector PQ, and I can find the vector PRQ, or I can say find PR and QR. So I'm going to find PR and QR. That means they all meet at that point. So if I want the vector PR, it's going to be vector PR. So that will be the position vector R, 0, negative 1, and 2, minus 1, negative 2, and 0. That's the position vector of vector P. This is OR minus OP. So this is going to give us the vector 0 minus 1 is negative 1. Negative 1 minus negative 2 becomes plus negative 2, that's 1. And 2 minus 0 is 2. So that's the vector PR. Then I also find the vector QR. So that's OR, minus OQ. So that one is also going to give us the position vector of OR is 0, negative 1, 2, minus the position vector of OQ is 3, 1, 4. And when we compute, we have the vector 0 minus 3, which is negative 3, negative 1 minus 1, that gives us negative 2, and then 2 minus 4 gives us negative 2. So these are the 2 vectors. Now we learn from our vector algebra that the cross product of 2 vectors give another vector perpendicular to the vector at the point of intersection of the 2 vectors. So these are the 2 vectors. So we want to find the cross product at the point of intersection of the 2 vectors. That will give us another vector which is perpendicular to these 2 vectors at that point. And these vectors are on the plane. So any vector perpendicular to these 2 vectors is the normal. So we find the cross product of PR and QR. So this is going to be I, J, K, that's the component vectors of the 3 directions S, Y, and Z. Then negative 1, 1, and 2, that is the PR. And the negative 3, negative 2, negative 2. And that is the vector QR. So if we find these vectors, we are looking at the determinant of these vectors. So this is going to be I, then open the brackets. So this and this is also, this time this negative 2 minus negative 4, which is negative 2 plus 4. Then minus J, this and this is gone. So you have negative 1 times negative 2, which is 2, minus negative 3 times negative 6, that becomes plus 6. Then plus the vector K. Don't forget they are unit vectors. So all these things are unit vectors. Vector K, so this and this is gone, so you have negative 1 times negative 2, which is 2, minus negative 3 times 1, that will be plus 3. So we are going to have 2I minus 8J plus 5K. So this is the normal vector. This is the normal vector. So at this point, we now use this one and one of the points, and I prefer the R, because that is where the 2 vectors meet, because that's where you find PR and QR. So they all meet at R. So this normal vector is at R. So we know the equation there. So this now becomes our vector V. That's the normal of the vector N, the normal vector. And what do you say? We say that the normal vector 2, negative 8, and 5 dot X, Y, Z. That is any position vector on the plane equal to the normal vector again, 2, negative 8, 5, dot the point that we pick, position vector, the point that we pick, that is K, so that becomes, sorry, R, so that becomes 0, negative 1, 2, 0, negative 1, and 2. So we know this is going to give us 2x minus 8y plus 5z equal to 0 plus 8 plus 10. So the equation of the plane is 2x minus 8y plus 5z equal to 18. That will be the equation of the plane. So this is the equation of the plane with all these points. Again, let's use GeoGebra to look at how to test it and see whether truly the plane will pass through these 3 points that we have. Okay, for this one I've already formatted my plane, so we are just going to type the equation straight away. So the equation is 2x minus 8y plus 5z equal to 18. So this is the plane. This is the plane. So I can just rotate it for you to see. And let me change the opacity. I said you right click on the plane, or you can right click on the equation and choose objective properties. So we go to the color and choose the opacity. I just want to choose this color and then increase this to the end, and I'll close the objective window. So you can see that this is the plane that I'm having over here. So what I want to do is to just plot the 3 points and see whether they are found on the plane. So the points are, the P is 1, negative 2, 0. So the point P is 1, negative 2, 0. So we plot that point, we see that it is on the plane, exactly on the plane, that's the point P. The point R is KO is 314, so KO equal to 3, 1, 4. And you can see that it's also there. Let's type the point R is also equal to 0, negative 1, 2. So you can check and see. The points are there. Let me change their colors so that we can easily see them. We highlight all of them, choose properties, or I can just drop the color here and choose any color I want. I want a yellow color. That is very obvious. So I have 3 yellow colors here. You can see all these points. If I rotate, you can see they are on the plane. And this plane passed through all these 3 points on the plane. So the vector that we obtain is coming from these lines joining them. So this and that and that and that. So let me change the color of this plane too for us to see. So maybe if I pick white and then probably increase the opacity here. So you can see that it is exactly on the plane here. And that is what we have. Let's look at another example. We have to determine whether these planes are parallel. We have 2 planes here. We want to find out whether they are parallel. In fact, the simplest way is to look at the normals of the 2 planes. And if the normals are parallel, then the planes too are parallel. If the normals intersect, the planes too intersect. So we wanted to determine whether the normals are parallel. So this is what we want to look at. So what are the normals? We said that the coefficients of x, y, and z is the normal vector. So it means that if you call this one L1, then the normal N1 is actually given by 3, negative 4, and 5. And if you call the second equation here L2, then the normal N2, which corresponds to that one, will become negative 6, 8, and negative 10. The question you want to find out whether these two vectors are parallel, and for them to be parallel, one is a constant multiple of the other. Now we can see that if I multiply n1 by -2, I'll get n2. So n2 is actually -2n1, or we can say n1 is actually -half n2. So since one is a constant multiple of the other, the two normals are parallel. So n1 and n2 are parallel. Therefore, the planes are parallel. So that's how simple again. So let's go to GeoGebra and see and check the verification. Okay, so we have our plane set up already. So we just want to type the two equations of the plane. The first one is 3x minus 4y plus 5z equal to 0, and that's the plane. So let's change the color and the opacity. So let's maintain this color but increase the opacity. So we come and type the second one. There will be -6x plus 8y minus 10z equal to 4 or minus 4 equal to 0. So let's change this color to red. Red will be okay, and then increase the opacity too. And let's check. Let me just rotate it. You can see that they are parallel, just one on top of the other, and you can see that they are parallel to each other. They are never touching. They are parallel. So you can easily see that from the view direction I've been chasing. So you can see that. So that is to show that these two equations, planes are parallel.